So what we're going to talk about now are the graphs of the remaining trig functions, which is cosecant, secant, tangent, and cotangent. So we'll start off by talking about the graphs of y equals to a cosecant of bt and y equals to a secant of bt. So just to point out, this doesn't really change, like the a and b really doesn't change from trig function to trig function. So this a is going to be affecting the y values, this b is going to be affecting our x values, or the t values in this case, which means it's going to be shortening or extending the period when you're graphing this. But the good news with this is, especially for the cosecant and secant, is if you can graph sine and cosine, then you can graph cosecant and secant. So that's the approach we're going to be taking. So let's start off by saying, look, when we're graphing, so when graphing y equals to a cosecant of bt, or y equals to a secant of bt, we will instead, or we will graph y equals a sine of bt, or y equals a cosine of bt. And I'm putting this just to say, hey, for cosecant we'll graph sine, for secant we'll graph cosine, and use these graphs to produce the graph of y equals to a cosecant of bt, or y equals a secant of bt. Okay, so here's the good news. If last section's notes were good, you know how to graph sine and cosine, then technically speaking you can graph cosecant and secant. So before we actually graph cosecant and secant, let me show you how we're going to use sine and cosine to produce the graphs of cosecant and secant. So here are the characteristics of cosecant and secant. Okay, so the first one is when sine of t or cosine of t equals to 0, this means that cosecant of t and secant of t are undefined. Now, why is that the case? Hopefully you understand why they're undefined. Because remember, sine and cosine, if they're 0, cosecant and secant is the reciprocal, which forces this 0 to go into the denominator. Okay, so what happens here is, see, if sine and cosine is 0, then cosecant and secant will be 1 over 0, because I'm just taking the 0 over 1 here and I'm taking its reciprocal, which that becomes a problem. So this implies, so why is it that these are undefined? In fact, let's actually kind of talk about this. So we could say, look, notice that cosecant of t is 1 over sine of t, and secant of t is 1 over cosine of t, right? These are the reciprocal identities we talked about earlier. So if sine of t and cosine of t equals to 0, this implies we are dividing by 0 for secant of t and cosecant of t, which makes them undefined. Okay, so now let's kind of talk about, okay, so what does that mean visually when they're undefined? Okay, so we would say, look, when a function is undefined, we say that it has a vertical asymptote. At that value. So what does that mean if we have a vertical asymptote? So we would say, look, when a function approaches a vertical asymptote, it either goes up or down forever. So it either goes up or down forever. And more importantly, we will never cross a vertical asymptote. Okay, so keep that in mind. We will never ever cross a vertical asymptote. So in other words, visually speaking, here's how it's going to look. Vertical asymptotes are usually vertical lines with that are dashed. So what is that? What that means is when the graph, when you approach the vertical asymptote from that one side, it's either going to go up forever or down forever. Now, we don't know, or we won't know until we figure out what the y values are, but something like this. Notice how these, as you get close to the vertical asymptote, it bends and goes down forever or up forever, and it'll never ever cross the vertical asymptote. You'll never cross it. Okay, so we'll see that actually now we just discovered that secant and cosecant do have vertical asymptotes. So when we put them together in the graph, we'll force them out, and you'll see exactly how it looks. So now the next part is when sine of t or cosine of t are at their maximum or minimum. And if you remember from the notes from last time, what are the maximums and minimums of sine and cosine? Which is plus or minus 1, right? If you remember, the maximum was 1, the negative was negative 1. Then we know that cosecant of t and secant of t share that point with sine of t and cosine of t. How come? Because 1 is just written as 1 over 1, right? So what's the reciprocal of 1? It's just literally 1. So notice how the reciprocal of plus or minus 1 is plus or minus 1, right? That's kind of what it is. So we notice that, hey, whenever sine or cosine hit a maximum, which is 1 or negative 1, secant and cosecant share that point with it because the reciprocal of 1 is 1. Same thing with the reciprocal of negative 1. So far, what have we discovered? When sine and cosine are 0, cosecant and secant have vertical asymptotes. When sine and cosine hit their maximums or minimums, those are also points on cosecant and secant. Okay, now the last fact, which kind of helps us put the graphs together, is that cosecant t and secant of t always open upward. At all maximums of sine t or cosine t, and open downward at all minimums of sine of t and cosine of t. Okay, the reason being is, see, when sine and cosine hit their maximum, they're at 1, and then they start getting closer to 0, and as they get closer to 0, the y values of the reciprocal become larger and larger and larger, which causes it to go up if it's positive, or if you're going from the negative towards 0, it causes you to go down. So what you notice is that at every maximum, cosecant and secant share the point with sine and cosine, and then they open upwards towards the vertical asymptote, and at the minimum they open downwards. So with these three facts, we'll be able to force out the graph of secant and cosecant. So let's look at one graph first. So let's just say graph y equals to cosecant of t over the interval 0 to 2 pi. Okay, so now instead of graphing cosecant of t, I'm going to graph sine t. But when I graph sine t, I'm going to graph it dashed because I don't want it to be included as a part of the graph. So when you're graphing sine to use to help graph cosecant, remember that this is going to be dashed. So if you remember the graph of sine, the points we used was what? 0, pi over 2, pi, 3 pi over 2, 2 pi, and then we had 1 and negative 1. So if you remember, sine was 0 here. At pi over 2 it's 1, which is its maximum, so it shares that point. So notice how I'm making that solid. At pi it's 0, 3 pi over 2 it's negative 1, at 2 pi it's 0. So the graph looks something like this. Okay, now I'm not going to notice how I'm making this dashed because I'm trying to tell the reader that, hey, this sine graph is not a part of the cosecant graph. I'm just using it to help me out. Now look, anytime sine is 0, cosecant is undefined, which means there's a vertical asymptote. So where is sine 0? At 0, so there's a vertical asymptote here. Where else is it 0? At pi, so there's a vertical asymptote there. And then at 2 pi, it's also 0, so there's a vertical asymptote there. So look, what do we know? This point, which is a maximum, cosecant shares it with sine, and then at a maximum, remember, cosecant always opens upwards. Now, since this is trapped between two vertical asymptotes, it's going to open upwards in both directions, and it's never going to touch the vertical asymptote. So guess what's going to happen at the bottom? It's going to open downward, and since it's trapped between two vertical asymptotes, it's going to open in both directions downwards, and it's never going to touch the vertical asymptote. So this is now the solid is the graph of cosecant. So notice how it's literally, once you graph this, then you can grab the cosecant, move it up, down, or whatever you need to do. So I always use the graph of sine to force out the graph of cosecant, then I go from there. Okay, so let's look at our second example. So let's create a graph of So for example 2, we're going to say graph y equals to 3 secant of pi over 2t, and let's do over the interval of, let's just say 0 to 2 pi. Okay, so here's what we're going to do. We're going to say, okay, well, now what we're going to do is we're going to say, so since I'm graphing secant, instead I'm going to graph cosine of t, and then I'll perform these operations for forcing it out. So graph of cosine of t, what is it that we know? Once again, we're going to use 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then what do we know? At 0, it's 1, at pi over 2 it's 0, at pi it's negative 1, 3 pi over 2 it's 0, at 2 pi it's 1. So if you remember, this is 1 period of cosine. Now where is cosine 0? At pi over 2 and 3 pi over 2, that means that's where secant is undefined, so which we have vertical asymptotes there, and at 3 pi over 2. And then remember, at a maximum, cosine shares that point, secant shares the point with cosine, but it opens upward, and since there's only one asymptote here, it's just going to open to the right and up. Now this one is trapped between two asymptotes. It's going to open down and in both directions. This one, the asymptote is to its left, so I'm going to go up towards the left. Here's 1 period of secant. So this is now the solid is the graph of secant of t. So now let's use the transformations like we did last section. So if I take care of the 3, what is this saying? This is 3 secant of t, which what happens, so let me actually move it down here. So the 3 secant of t is just saying grab all your y values and multiply them by 3. So at 0 this was 1, so at 0 now it's going to be 3. 1, 2, 3. At pi over 2 I still have a vertical asymptote. Vertical asymptotes stay unchanged, so it'll still be a vertical asymptote. At pi it was -1, so if I multiply by 3 now it'll be -3. 3 pi over 2 we had a vertical asymptote, and at 2 pi it was also 3. Okay, and if you remember now it opens upward, downward, to the left. So this one is what? This is the 3 secant of t. Now finally, to take care of 3 secant of pi over 2t, what we're doing now is, this is saying do what? This pi over 2 is saying grab all of your x values here and divide them by pi over 2. Okay, so if I divide them by pi over 2, or in other words, if you think about it, when I say pi over 2 divided by pi over 2, I could also say multiply by the reciprocal of pi over 2, because I'm saying a fraction divided by a fraction. So in other words, here's what we're saying. Our x values won't change, or our x values will change, our y values won't change. So I'm going to put these 4 values here, but they're going to change. So pi over 2, when I divide it by pi over 2, what does that become? That becomes 1. And at 1, now we have our vertical asymptote. At 0, when I divide it by pi over 2, it's still 0. It's 3. So this is still going to go up. At pi, if I divide it by pi over 2, what does that become? That becomes 2. And at 2 now, it's the y value doesn't change. Remember, it's just the x values, -3. At 3 pi over 2, if I divide it by pi over 2, that becomes 3. And I think you're starting to see the pattern here. And then at 2 pi, if I divide it by pi over 2, that becomes 4. And at 4, my y value is 3. So it looks like this. Which, notice how this still fits in one period of secant, but because since b is pi over 2, if you remember for sine and cosine we said the period was 2 pi over b, same thing applies to this. Okay, so to find the period it's still 2 pi over b, because secant and cosecant are literally the reciprocals. Okay, so those are 2 examples where we took into consideration the graph of secant and cosecant, and I'm sure you'll have plenty of practice of those on your homework. So now let's talk about the graphs of y equals to a tangent of bt and y equals to a cotangent of bt. So once again, a is saying we're going to multiply to the y values. This b, what are we doing? We're going to be dividing by b to all of our x values. Okay, so now unfortunately tangent and cotangent don't have the same key values of sine and cosine. Okay, so let's talk about the characteristics of these, of y equals a tangent of bt and y equals a cotangent of bt. And we'll talk about the characteristics, and then we'll use this idea to graph a few of the tangent graphs and cotangent graphs. So the first fact I want to talk about is that a period of tangent of t and cotangent of t starts at a vertical asymptote and ends at the next consecutive asymptote. So this is kind of good news, because what is it that we know? And we know that from previous experience that, hey, there are values where tangent and cotangent are undefined, which means visually speaking, that's where we have our vertical asymptotes. So the good news is, whenever we graph our sine and cotangent functions, we'll start from a vertical asymptote and we'll end at a vertical asymptote, and then whatever the graph looks like in between, that's what one period of tangent and cotangent is going to be, which that's good news. So we know that we're always going to start with a vertical asymptote and end with a vertical asymptote for tangent and cotangent. So next thing I want to talk about is that the period is found by P equals, and it's going to be very similar to sine and cosine. If you remember, for sine and cosine it was 2 pi over b. However, for tangent and cotangent it's pi over b. Okay, so now what we know is, just to kind of talk about this again, this letter A, this is the vertical stretch or compression of tangent of t, cotangent of t, okay? And then B is the horizontal stretch compression of tangent of t or cotangent of t. So for this one, we multiply y values by a. This one, we divide x values by b. Okay, so that's basically what the a and the b in this equation up here are telling us to do. Okay, so the third thing, which is the key values, which is what we're going to use for tangent of t and then cotangent of t. Now unfortunately, the key values for tangent of t and cotangent of t, they're not the same, right? For cosine and sine, if you remember, they were the same, but tangent and cotangent are undefined at different places. So for tangent of t, it's negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. And negative pi over 2 and pi over 2 is where tangent is undefined, and you'll see why we care about these, or why these values are preferred. Tangent of negative pi over 4, that's negative 1. Tangent of pi over 4, that's 1. Tangent of 0 is 0. So once again, the values we're picking are producing outputs that are either negative 1, 0, 1, and then they're undefined. So for cotangent, the key values are 0, pi over 4, pi over 2, 3 pi over 4, and pi. So notice how we're starting from 0, we're ending at pi, which is 1 full period. Negative pi over 2 to pi over 2, that's a distance of pi also. So once again, cotangent is undefined at 0, undefined at pi, 1 at pi over 4, 0 at pi over 2, negative 1 at 3 pi over 4, and so on. Okay, so just remember that. One comment I want to make: if the period is other than pi, then these values are going to be adjusted. How are they going to be adjusted? Well, this value b, remember, you'll be dividing these guys by b, which will give you your new adjusted values. And we kind of do that with transformations. They work out nicely anyway. Okay, so let's look at our next example. So we're going to say graph y equals to tangent of t and y equals to cotangent of t. Okay, so let's start off by graphing tangent of t. And what were our key values? If you remember, we start from, and once again, they're all equally spaced out, so you don't have to worry about the spacing as long as you stay consistent. Negative pi over 2, negative pi over 4, pi over 4, pi over 2. Okay, so if you think about this, so let me show you guys, let's just draw the unit circle here and show you how tangent and cotangent, or y tangent is undefined. So negative pi over 2 would mean where? In standard position, that would put us here. Now I'm rotating, right? So that point has coordinates what? 0, negative 1. And if you notice, tangent is y over x, negative 1 divided by 0. And when we divide by 0, we have a vertical asymptote. So that's where we are. So negative pi over 4 puts us here, but we get a 45, 45, 90 triangle. So what would this be? This would be 1 over rad 2, negative 1 over rad 2, and then tangent is what? Y over x. So negative 1 over rad 2 over 1 over rad 2, that's negative 1. And then tangent of 0 is here, which those points are 1 comma 0, so 0 over 1. As long as I'm not dividing by 0, we're good. So 0 divided by 1 is 0. Pi over 4 puts us a 45, 45, 90 triangle up here, which is going to be the same thing as 1 over rad 2 divided by 1 over rad 2, which is 1. And then at pi over 2, we get it undefined. So then the graph of this, now look, the graph of tangent is not linear. It's kind of bent, right? So notice how I'm adding this bend. And what is it that I know? As I get close to the vertical asymptote, it's going to bend and become more vertical. Same thing down here. It's going to bend and become, so it kind of has this shape. So that's one period of tangent. Now for cotangent, it's identical, except now our key values are going to change. So this will be what? 0, pi over 4, pi over 2, 3 pi over 4, and pi. And once again, at 0 and pi, we have vertical asymptotes, because if we always start and end at a vertical asymptote, the period does. At pi over 4, cotangent is 1. At pi over 2, cotangent is 0. 3 pi over 4, cotangent is negative 1. And so now it kind of has this feature of it. And then you go up like that. Okay, so notice how tangent and cotangent are similar, but they're kind of like cotangent and tangent are flipped, right? That's the whole reciprocal feature. Okay, so this is what the graph of tangent and cotangent looks like. But in all honesty, if you can graph these, then you could graph any variation of tangent and cotangent. So let's actually do one where we'll see a variation of it. And as always, I'm going to use transformations to do this. So for example 4, I'm going to say graph y equals to 1/2 cotangent of 2t. So let's not worry about the 1/2 and the 2. See, this 1/2 is saying what? Multiply all your y values by 1/2. This 2 is saying multiply all your x values, or the t values, by divide them by 2. Okay, but to do this, I'm going to first start off by graphing cotangent of t. And if you remember, we just did this. So at some point, I mean, once you get the hang of it, I think it'll be very straightforward and quick for you. But it'll be these values, and we're only graphing one period. So that's vertical asymptote there, vertical asymptote at pi. At pi over 4 it's 1, pi over 2 it's 0, 3 pi over 4 is negative 1. So my graph looks like this. So then we can say, okay, look, now let's graph cotangent of 1/2 t. Okay, or actually let's do the 1/2 on the outside, because this, I always work with the y's first, then with the x's. Not that it matters. So this 1/2 outside is saying what? Grab all the y values of your points and cut them in half. So remember, vertical asymptotes are never affected. So this is going to stay 0. This is going to stay pi. Okay, as long as you're multiplying to the y values, vertical asymptotes aren't affected. So at pi over 4, instead of 1 now, it's going to be half, right? Because it was 1 here, I'm cutting it in half. At pi over 2, it's still going to be 0, because 0 times a half is still 0. At 3 pi over 4, since it was negative 1, now it's going to be negative half, which now looks like this. So it kind of got pushed, right? It got compressed upwards. That's what happens to this. So then lastly, what is it that we need to take care of? We need to take care of the 2t, which means this becomes 1/2 cotangent of 2t, which is saying now we're going to go to this graph, and what are we going to do? We're going to divide all the x values by 2, or instead of dividing, we could also say we're multiplying them by 1/2. Okay, so notice how over here this has an x value of 0. You multiply 0 by 1/2, it still stays 0. At pi over 4, we multiply pi over 4 by 1/2, we get pi over 8. And the y value here was 1/2, which the y values don't change now, right? Because we're just changing the x values. At pi over 2, it was 0. If I multiply the pi over 2 by 1/2, it becomes pi over 4, which is 0 now. And by the way, the spacing here, don't worry about it. As long as you keep them the same, we have nothing to worry about. This was 3 pi over 4. If I multiply that by 1/2, it becomes 3 pi over 8, which is at negative 1/2 now. And then lastly, the pi divided by 2 becomes pi over 2. And so now we have completed one period of cotangent of our graph. Now look at what our period is. We start at 0 and end at pi over 2. So this is a period of pi over 2. And notice how because of that 2, because what was the period of tangent or cotangent? It was pi over b. What's b here? B is 2. Notice how this is saying, hey, if you have cotangent of 2t, your period should be pi over 2. And when we made the adjustment, it worked out just fine. Okay? So, now the next graph I want to talk about is now we're going to say, and this will be our last example, so find the equation of y equals to a tangent of b t. Okay, so the first thing we want to do is, let me first give you the graph. So these graphs are given. So let me draw these vertical asymptotes. So this is negative 2 pi over 3, 0 goes up and down. Goes up and down. This is 2 pi over 3, 0 goes up, and then this y value is, that right there is pi over 2 comma negative 2. Okay, so we could see that one period of this. So let's go after the b first. We could see that one period of this is what? See, this 0 and that 0 starts repeating, and that I've traveled from 0 to 2 pi over 3, so we know that the period is 2 pi over 3. So we can use this to help us find b, because what was the period, what was the formula for period? It was pi over b. And we know p, which is 2 pi over 3, so it'll be 2 pi over 3 equals to pi over b, and now I'm going to solve for b. So if I cross multiply, I get 2 pi b equals to 3 pi, and if I divide by 2 pi, I get b equals to 3 over 2. Okay, very good. So now this formula can now be updated to what? Y equals to a tangent of 3 over 2t. Now we could easily find a by doing what? See, this is t, that's y. So I could replace y with negative 2 and t with pi over 2 and solve for it that way, which will help me find a, right? It's kind of like an equation where I'm just plugging things in for it. So if I replace y with negative 2 equals to a, and see, why don't I want to use these points? Because y is going to equal out to 0, and it's just going to clean everything out. It's going to make everything 0 out. So we want to pick a point that we don't have 0 for y. So then we get a times tangent of 3 over 2 times, and what is t? Pi over 2. And so this becomes, I'm running out of space, so I'm going to move to the left, negative 2a, or negative 2 equals to a tangent of 3 pi over 4. That's what it becomes. And we know that tangent of 3 pi over 4, we could find that. I already know what it is. It's actually going to be this right here. If you're not sure, you could draw your right triangle and find it, but I'm going to tell you it's negative 1, because at this point I have this down. And you will get to the point also where the ones with the nice reference angles you'll know right away. So if this is negative 1, what does this become? Negative 2 equals to negative 1 times a, which is negative a, which means a equals to 2. And if a is 2, then I can go ahead and update this equation, and then we're done. So y equals to 2 tangent of 3 over 2t. So for this one, we were given the graph and we're asked to work backwards, and we found the a and the b to finalize this. Okay, so this takes care of the graphs of secant, cosecant, tangent, and cotangent. There's a lot going on, so I would highly recommend you go back and look at your notes, but the key values are important. You have to make sure that you know which key values to use for tangent, cotangent, and sine and cosine, and so on. And for secant and cosecant, the good news is for sine, cosine, secant, cosecant, they're all using the same key values, and tangent and cotangent have their own different key values. So technically speaking, there's just 3 sets of key values you need to know, and these will show up on the exam. You are expected to know how to graph these trig functions on the exam, so just make sure that you have this stuff down. And if you don't hesitate to reach out to me and email me with questions or show up to my office hours, and I'll help you out.